today is top-part forward-backward symmetry and an Axigluon explanation. So this is the project working with Xinjia and Michael. So this is the outline of my presentation. First, I will talk about what is forward-backward symmetry. Then I will introduce the new particle Axigluon in our model. And also I will talk about the experiment constraint, that is the Axigluon surface law. And also I will describe the model we built up. And at the last part we will talk about the result we get and the conclusion. Okay, so at Tevatron, the forward-backward symmetry is defined as the number of forward event, the number of top part going to forward minus the number of top part going to backward, divided by the sum of total events. And by the forward events, we mean that if the polar angle between the momentum of the top part and the momentum of the proton beam this polar angle is smaller than 90 degrees, then we will consider this as a forward event. And vice versa will be a backward event. Okay, so about 1 year ago, Tevatron has measured the asymmetry around 0.164. And this is approximately 2 sigma away from the standard model prediction. And what's more interesting is that the size of the forward-backward symmetry grows with the environment mass of the event. So that's the main motivation we have to consider a heavy Axigluon, which the mass of the Axigluon should be larger than 800 GeV. And here is a plot for the simulation of the Axigluon with mass 1.1 TeV, and axial coupling is equal to 1.1. And the black dot is experiment data, and the blue line is the simulation. We can see that for this kind of parameter, the Axigluon can generate the forward-backward symmetry very close to the experiment data.
Do they quote a p-value for that plot? Because it looks like from that plot that it's more than 2 sigma.
Yeah, I was going to ask the same question.
From
this plot?
Yeah, because I mean, if you just count the total number, you're saying it's 2 sigma. But if you actually fit this distribution,
I guess in their experiment paper, they list the standard model prediction is around 0.08, something like that. So it's around.
I mean, maybe the way to think about it is, well, look at bin by bin. It's sort of 2 sigma, 2 sigma, 2 sigma. I don't know. This is somehow a weighted average of all of this data, right? And
it doesn't matter. You're saying if it's just if the average deviation in each bin is.
Maybe it's 2 sigma
Yeah,
flat.
maybe. Yeah.
I don't know. But you're right, though. At first glance, you look at that and say that looks pretty consistent.
Yeah, maybe you're right. Maybe it's no better. It's no stronger. Okay.
Okay, so since we know that the Tevatron has been shut down, and this asymmetry is already with the full data set, so we know that this asymmetry won't disappear in the future. So, and also there are many other models trying to explain this asymmetry, but most of the models with T-channel T-channel mediating particle have been killed by the constraint from the LHC data. And also the S-channel models with a light particle with narrow width also have been killed by the digest search, and also are discovered by the feature we see in the previous plot that the size of the symmetry grows with the environment mass.
Are you going to say anything about D0? What's D0's final statement on this?
I don't know.
They found a similar 2 sigma deviation.
In the past, they had a somewhat lower value On
It is a
CDF,
little-
it was tough to compare. I think CDF's value went down in the very last iteration compared to what they had previously. So did D0 stay the same, or? I just.
It would be good to know.
Yeah.
Okay.
I don't.
So, okay, so what is an Axigluon? The Axigluon is a massive spin 1 color octet which has the same quantum number as a QCD gluon. So why we want it to have the same quantum number? The reason is because there is a TT bar cross-section constraint which is very strong. So that leads us to consider that the asymmetry should be generated from the interference between the new physics and the same model. It cannot be generated from the new physics only. So we want to have an interference so that we need to, the Axigluon have to have the same quantum number as the gluon. And also we will consider the Axigluon is heavy, which is around 1 TeV.
Sorry, I don't, why is it that the constraint is easier to satisfy if it's interference?
Oh, it's because also here we can see that at the larger environment region, the size of the asymmetry could be very large. And if we want to generate such large asymmetry, then maybe we need, if we wanted to generate only from new physics, we would need to, this amplitude should be very large. But then, since Axigluon contribute to PP bar to TT bar, so it will contribute more to the TT bar cross section. So that would make the TT bar cross section doesn't agree with the experiment data.
So, just may I understand? So you're saying you try not to change the overall TT bar cross section, but you're just trying to change the symmetry, and that's why you need interference?
Yes, so we do not want to change the total TT bar cross section very dramatically. So we just want to change it by a little. But at the same time, we want to generate a very large asymmetry. So we want the asymmetry to be generated from the interference. So here is a tree-level cross-section for QQ bar to TT bar with an Axigluon. And the interference term is given by the third line here. And from this formula, we can see that since the polar angle theta, here C is this quantity. So if we wanted the asymmetry to be positive, as we see before, since here there is a negative sign, so we need to have the product of the axial coupling, the Axigluon, the right part and the top part should be smaller than 0. Okay, so that's one condition we need to satisfy when
So
we build.
that term in parentheses is positive?
Yes, so that this total term is positive.
No, but the term in parentheses has got lots of minus signs in it. Is it obvious that it's positive?
Oh, so in the first step, we just make this vector coupling be 0.
Okay.
Yeah. So and also since we consider heavy Axigluon, that means this quantity should be larger than the S head in temperature. So in order this total quantity to be positive, this
So
should
for
be
large MG, it's clear.
yeah. So, and also we can see that the size of the asymmetry also is approximately linear to the product of these two couplings. And also if we increase the coupling, vector coupling of the Axigluon to Quarks, then the size of the asymmetry will be diluted due to the sign here. Okay, so next I will talk about the experiment constraint. So here are the four experimental constraints we considered. So the first is TD by resonance constraint. So here is a plot from the CMS paper, and the black dot is experiment data, and the red line is standard model simulation. So we can see that at the low environment mass region, the experiment data agree with the standard model prediction very well. So that means at low environment mass region, the Axigluon will suffer from the resonance constraints strongly. And also, see here is a plot of the simulation for standard model spectrum and Axigluon mass equals 1T with different weights. So here we can see that one way to relax this constraint is to make the weight of the Axigluon to be larger. So this corresponds to a weight of 118 GeV, and this corresponds to a 300 GeV weight. So the larger the weight, it can agree with the experimental data better. So next constraint is digest resonance. So here, this plot gives the Atlas 95 confidence level upper limit for the new physics cross-section. And so I just do the simulation for the Axigluon and compare to the Axigluon's cross-section to their upper limit. And this is the Axigluon with standard coupling, which the axial coupling equals to 1, and the vector coupling equals to 0. And for this coupling, we can see that the Axigluon with the mass smaller than 40 weight will be ruled out by this digest resonance search.
Is this one sensitive to the width or not so much?
This one is not sensitive to the width as before because it's related to their search strategy. So they just count the number of events fall into the 0.3 mass region. So it's a very wide.
Plus or minus 30%.
Yeah.
Basically. Okay.
And this is for all the jets. It's the
This is for
or the
Digest.
yeah.
I see.
The next is the digest angular distribution. So for the digest event from the QCD process, so since it's a T-channel process, so we expect that the outgoing jets would mostly go into the forward direction, and this will result in a flat distribution on chi. So chi is defined here as the exponential of the difference in the velocity of two outgoing jets. And however, if the event is coming from the exchange of S-channel Axigluon, then the event will have an isotropic angular distribution, and this will result in a peak at the low chi region. So we just do our simulation, use the first 4 chi beams data, because that's the region sensitive to the new physics.
That dashed line is a
That's
signal from the 4TeV.
Yes,
Right.
here.
Same couplings as the previous, as the digest one. The same
Oh.
couplings, same.
This is the experimental paper, not the
Oh, this
simulation.
is some other model.
Yeah, yeah.
So you're going to fit the shape?
Yes,
The shape analysis.
in the digest angular distribution constraint, I'm just fitting the shape of the first 4 chi beam.
I see.
Chin, you probably talked about this. So when they do the analysis, this is assuming one of them decays with the lepton, so that you know the difference between the T and the T bar always?
This is digest, so you do not need to know the sign of the jet. So for the TT bar, yes, you need to at least one top pass, one W balsam going to lepton decay.
Oh, and this is just the absolute value of the.
We're just measuring the production
Yeah,
of
yeah,
vertex, right?
okay, thanks.
Okay, so in order to have a massive vector boson, so we need to extend the standard model gauge group to a new group SU31 cross SU32, and then break it simultaneously with a complex scalar field transformed as 3 and 3 bar under this new group. And then we can write down the kinetic term of this new scalar field, and then get a massless gluon. Then we'll get a massless gluon and a massive Axigluon. And this is the Axigluon, which the mass of the Axigluon is given by here. Theta is the mixing angle between these two gauge groups. And F is the web of the scalar field. Okay, so before I said that in order to have a positive asymmetry, we need the product of these two couplings to be smaller than 0. So that means the light part and the top part should transform under this new group differently, and that will give an anomaly if we do not introduce new particles. So in order to cancel the new particle, in order to cancel the anomaly, we need to introduce new particles. So here we introduce two new particles which transform as the right-hand top part under the electroweak gauge group. And with the new vector light part, we assign their transformation property like this under the new gauge group. And here I just list the coupling of the Axigluon to the light part and the top part. And we can see that they are the function of the mixing angle theta, alpha, and beta. So then we have the freedom to change the Axigluon's coupling to upper part and top part differently.
Sorry, what are alpha and beta? Sorry.
Alpha and beta are just the mixed angle between
so
the
the mass and the formula.
yeah. So and with such assignment, we know that the theory is anomaly free.
So this anomaly is for which gauge symmetry?
It is for the extended gauge group SU31 cross SU32, because if we want
Oh, I see. So the mass of this anomaly compensator only needs to be lighter than that scale. So it's no, sorry. Yeah.
I'm guessing the anomaly is SU3 squared U1 hypercharge, right?
yes.
That's probably the anomaly that's not true. Right?
I see.
Okay, so since we know that the size of the symmetry is proportional to the product of GAQ times GAT, so we want the product of GAQ and GVT to be as larger as possible. GAQ and GAT to be as larger as possible. And also we know that the vector coupling dilutes the symmetry, so we want the vector coupling to be as smaller as possible. So we just choose our mixing angle as this in order to have such property. So the weight is given by this formula after we choose this coupling.
Sorry, so this limit is chosen to do, you've made two choices here, so you've chosen this to make two things happen, right?
Yeah.
What are those two things?
So The first condition is we want the GAQ times GAT as larger as possible.
Okay.
And also we want GVQ and GVT as smaller as possible. And also we want GAQ to be smaller and GAT to be larger.
But morally speaking, you just maximize the asymmetry, basically. These are just the parameters. Of
Maximize the asymmetry while lose the digest resonance constraint.
Oh, I see. Because the digest resonance constraint is coming dominantly from the why? How does it minimize the digest constraint?
Because it's the strongest constraint in most of the parameter region.
Right, but what are you doing to weaken the digest constraints?
Because digest constraint is proportional to GAQ. So we just
Oh, I see. So right. So you're trying to cut that down. Okay. Got it.
okay. So here is the result for the general effective model and the UV complete model with the build up. So the blue shaded region is the fit to the CDF asymmetry data, and this yellow dashed line is the total TT bar total cross section, and this red line is the TT bar resonance constraint. The black dotted line, black dashed line is the digest angular distribution, and the orange solid line is the digest resonance constraint. So we can see at the low mass region, TT bar resonance constraint is the strongest. But when you go to higher mass region, the digest resonance constraint will be the strongest. And for the general theory model, effective model, almost all the allowed parameter region are ruled out by the experimental constraint. However, after we introduce the new particles, so we have the freedom to change the coupling independently, so we can relax the digest constraints. And here, this is the axial coupling, this is the mass. But here, since all the coupling is a function of the mixed angle theta, so here I just list as theta. So we can see that the digest constraint is relaxed. So that gives us a sizable part of the parameter region are survived from the experimental constraint.
So maybe I don't understand. I guess I want to understand what the difference between these two is. I guess maybe what exactly is the difference between these two models, and what is it that's relaxing the constraint?
Oh,
The second one.
so
what's the difference?
this one is a model we just choose that the GAQ to be negative GAT and all the vector coupling to be 0.
And then you plug into that formula you wrote at the beginning. This is a choice of parameters in that big formula.
Yes.
And then you do the fit to that.
Yes.
Okay.
And this one is, since we know that for this one, all the coupling is a function of theta. So there is only one degree of freedom, which is theta, and also the mass of the Axigluon.
But what is it that's relaxing the constraint compared to the effective field theory?
Oh, because
What physical processes? Yeah, go ahead.
because since we introduced two new particles, so we have two new degree of freedom, alpha and beta, the mixed angle. So we choose that in order to make the GAQ to be smaller, so that it will relax the digest resonance constraint.
So, but couldn't I have made that choice in the effective theory? I mean, I'm trying to understand why you were able to do something here that you weren't able to do there. Is it just a bad choice that you made?
You shouldn't call it a general. It's a particular choice. Chooses these two couplings to be equal.
Oh yes.
So it's maybe okay. But you could have made, inspired by this model, for example, you could have made a different choice and got a plot that looked a lot like this.
Yes,
Is that right?
Michael is doing that. Michael is scanning all the parameter space.
Okay.
Yeah.
So I mean, but just to be absolutely clear, this thing just contains some additional heavy states compared to that, and those heavy states presumably don't contribute much to the experimental constraints. Is that right? So
Yeah, it's
Is
just
that right?
allow more general coupling. To have these four couplings, like GAQ, GVQ, GAT, GVT.
but I mean,
Plus
for the
mass.
for the phenomenology, you could have just worked with that formula and chosen arbitrary couplings.
So,
Okay,
okay, otherwise it's.
got it.
So here are the parameter space that are survived from the experimental constraint. But we can see the constraint of the TT variant is still very strong. And also if the mod and mod LHC budget resonance constraints are given, then maybe this parameter space will be ruled out in the future. Okay.
Sorry, is it without above or below? I'm just kind of missing.
Do you mean what's the
Which
shape?
side of the line is actually excluded?
Oh, the upper part of
Okay.
Yeah. Okay, so here is the conclusion. So we have seen that the top part forward-backward symmetry is still unsolved. There is no proper explanation for this asymmetry. Yeah. And most of the models have been killed by the LHC constraint. And the CDF forward-backward symmetry data showing since the size of the symmetry grows with the environment mass, that means maybe the heavy Axigluon would be preferred. And also from the result, we can see there is a small part of the region still allowed, but maybe excluded in the future. So that's my talk.
So isn't there also, there's also an, what is it, a charge asymmetry that you can measure at the LHC?
Yes.
That you didn't talk about. Is
But-
that going to be competitive?
Right now, the charge asymmetry, since the uncertainty is very large, so the charge asymmetry is still consistent with the standard model. So
But that doesn't place a constraint on this model?
that doesn't place a strong constraint. Maybe just rule out a little region.
I guess another question I had, I guess I had the impression from years ago that it was, from quite a while ago, that it was a very, very tight game. And somehow, I mean, I don't remember plots with this much of a, your last plot basically where you showed, right, the plot on the right there. I mean, it's a good sized region of parameter space where you say everything works great, all the constraints are satisfied. But I thought I remember it was already a tighter game a while ago. I mean, is that because the number, the asymmetry number came down a bit from CDF?
Yes, the
Is that
asymmetry.
important? Is that the case? That's actually very important for that?
Yes, the asymmetry is getting smaller, and also the standard model, the higher loop standard model prediction is getting a little bit larger. So if you include the standard model contribution, it would make the asymmetry, it would make this blue shaded region larger.
I mean, is it possible that if you did a really, really, really careful job of the blue region, it would be already a lot smaller? In other words, I'm just asking sort of how confident are you that the blue region doesn't go up to those red and orange lines in that plot, for example?
I'm not very confident about that.
I guess the less confident part is this constraint, I would say. Fitting the symmetry is easy, right? You really know how experimenters do this constraint is hard. You
I
want
thought
to do
you just-
exactly the
I
same.
thought you just predict how many things they have in the different bins, and you know what, I mean, the acceptance.
For this region, I would be less confident about these solid, these curves rather than the region.
Why?
Because the external constraint that come, we cannot reproduce everything what they do.
So one thing is that for all the digest constraint, since if we, so I'm doing all the constraint with the MATLAB simulation. If we do the simulation very careful with just the standard model gluon and Axigluon interference to produce the digest constraint. So most of the event will be from the standard model gluon process. That will be dominant. So in order to do an efficient job, we just make a approximation that we just generate the Axigluon only events in all the digest process. Yeah, so that's a very strong approximation, I guess.
What you're neglecting is the interference, you mean?
Yes, we
Yeah.
only generated the Axigluon.
I see. But so that you would say is the major uncertainty? Because I thought you also said we don't know what the experimentalists do, which sounds like maybe you don't know what the efficiencies are for your signal to be counted, right?
Digest, how do you reproduce their result? Are you going to simulate all the QCD digest events?
No, but what you could do is you could...
You generate most of them forward direction, and then explain the result.
Because you're saying because the kinematics is different from the models that they...
Yeah, also, of course, acceptance, efficiency, all these things cannot be completely...
Well, if you have a signal
It's
model
higher
which is
order
similar to their
correction.
signal model, you can compare those, right? So if you have a signal...
For
the
example,
kinema-
these K factors, how do you use, right?
Right.
That's correction. Since I cannot compare our standard model with their standard model, there's no way we generate so many digest events from the standard model.
Yeah, except, I mean, ideally, you're supposed to be able to just compare signal models to signal models, right? I mean, ideally, should give you enough information about acceptances that you should be able to take a number of Monte Carlo events and turn it into a number of experimental events, and that's all you need to set a limit. So I understand there's the interference issue. That really is a theoretical uncertainty. K factors, that's just a theoretical uncertainty on your rate, right? But then, then I'm trying to understand, are you also saying that the kinematics of your signal is different from the kinematics of the signal that was searched for in these experiments?
They do contracting action.
And this is more forward, so you're saying that it's also the kinematics of your signal. Okay.
So what do you actually do when generating these events? So do you multiply by a K factor?
I think you did multiply by
Yeah.
some K factor.
For the TT bar total cross section, we just multiply a K factor we get from a theoretical calculation paper. And for the digest process, we didn't multiply the K factor yet.
But the TT bar resonance should be okay, no?
Yes, the TT
That
bar
one should be
resonance.
okay.
Yeah.
But the digest ones, seems like it might be worth, talking to the people that do the searches and see if they'd be willing to put your model into their searches, right?
Yeah.
I mean, it seems like it's different enough. It seems like it would be worth it to do that. Any questions not by me?
Well, I had a sort of basic overview question. So, I'm just not having connect between the parameters of Lagrangian, and you gave me the cross section and had the cosine factor, but basically just how is it that the relative sign leads to a certain angular distribution? I mean, what's I'm assuming I'm doing this going past fast or something, but other than just looking, okay, there's a cosine factor, cosine theta
Yes,
factor.
here C is the cosine theta. The theta is the polar angle.
Yeah, but why, basically, in a
So,
physical sense?
that means if the event is in forward direction, so theta should be smaller than 90 degrees, cosine theta should be larger than 0. So if we and also the size of the forward-backward symmetry is positive. So that means more events are going to forward. So for the positive C, the cross section should be larger. That means GAQ times GAT should be negative.
No, I get that. I'm trying to thinking of it like what actually what is the steps of the reasoning?
Oh, okay. So.
Don't need to show the spot, but
Yeah,
it's not connecting my.
Yeah, I remember the one Xinjia explained this to us. He just draw a picture to show this, how to reasoning this. So, GAQ. So, for example, we just choose that if GAQ larger than 0, and also GAT larger than 0, right? So we just choose an example to say what will this coupling lead to. So, and we just choose GLQ larger than 0 and GRQ equal to 0. So since GQ is GLQ minus GRQ, right? So we just have this to give that. And also, similarly, we have GAT larger than 0, or GLT larger than 0, and GRT larger than 0. GRT equals to 0. So the Axigluon only couples to the left-handed quarks. Then we draw the classic picture that this is a quark, this is the anti-quark, and we consider the Axigluon exchange process. So the Axigluon only coupled to left-handed quark and left-handed anti-quark. So the spin, then we can know that the spin direction is left-handed, so the spin direction is this, and the spin direction is this for the incoming quarks. Because now we are consider the Axigluon mediating process and only coupled to the left hand. And also we know that, so for example, we consider the positive event. So this, for the positive event, this should be a top quark. For the forward event, this should be a top quark, and this should be an anti-top. And since Axigluon only coupled to left-handed top and left-handed anti-top, so we know that the spin direction is this, and this spin direction is this. So for this spin signs, the amplitude for the forward event should be larger than the amplitude of the backward event, right? And also, since the asymmetry is generated from the interference between the standard model and the Axigluon, right? So if the Axigluon the amplitude from the Axigluon can cancel the amplitude from the standard model, then there would be a larger interference effect, right? And also because the propagator of the standard model is just 1 over q squared, and the propagator of the Axigluon is q squared minus m Axigluon mass squared. And this is smaller than 0. This propagator is smaller than 0. This is larger than 0. So there is a relative sign between these two amplitudes. So if we have this kind of coupling, then the amplitude of the Axigluon going to the forward direction would cancel this standard model. That would make the total amplitude be smaller. That means the number of events going to the forward direction would be smaller, would be less than the number of events going to backward.
Maybe the opposite way.
Yes. So then we know that in order to make the number of events going to forward
Right, yeah, okay, yes.
small, then we need to flip the sign of one of these coupling.
Okay, thanks.
Thank you. surprised that the experimentalists and researchers are still they're not looking for Axigluon. I mean, they should, right? The digen resonances and the